Today I will make a presentation about magnesium silicon dioxide nanocomposites. Actually, I will refer biomedical applications and especially prosthesis applications. Basic definition of prosthesis is artificial device which substitute for a missing body part. Because of the development of amputational surgeries in 18th century and horrible consequences of World War I, the research on the prosthesis increased. We can see soldiers with leg prostheses. However, using prostheses inside the human body is a relatively new topic. Also, using different materials in the human body required material science and biomedical cooperations. One of its good example is, as we remember from our material science class, after the first total hip replacement in 1974, doctors realized that bone tissue was diminished by the bone eater cells. After consulting and cooperating with material scientists, they realized that bone eater cells were induced by particles that rupture from the plastic part because of the wear caused by walking. By giving energy, they made a cross-linked plastic which is relatively hard and resistant to wear, and they solved the problem. Nowadays, scientists use very different materials for biomedical applications, and we can see these materials on the table at right. Besides that, scientists expected that over 40 years, 90% of the population will suffer from the joint diseases, which means material science keeps its importance in the future. Our material magnesium is a lightweight metal, which is the ninth most abundant element in the world. Because of its good mechanical properties, it's the third most used structural metal after iron and aluminum. Since it's the lightest metal available for engineers, in history it's used in military aircrafts in Germany during the war times. Also today, in order to reduce weight and increase efficiency, car manufacturers use magnesium and magnesium-based alloys for low temperature components because of its low melting temperature. Human body also contains magnesium, and more than necessary magnesium can be discarded from the body by urine. Most of the metals used for biomedical applications such as stainless steel, titanium, and cobalt has different mechanical properties than human bone. This difference causes stress shielding effect, which is the changing of bone density because of the materials, because of the different stress levels on the bone and prosthesis. However, magnesium and magnesium-based alloys have more similar mechanical properties. Also, biodegradability and biocompatibility properties of magnesium make later surgical interventions unnecessary. Normally, temporary implants should be removed from the body after about 1.5 years. But low strength, low fatigue resistance, rapid degradation inside the human fluids limits the clinical applications of magnesium. Particle reinforcement by silicon dioxide may change this. As we can see, adding silicon dioxide 0.5, 1 and 1.5% volume change texture. X-ray diffraction shows strong bezel texture in pure magnesium, but by adding silicon dioxide, intensity in the pyramidal plane increase. These results show that nanoparticles dispersed in the magnesium more randomly. This uniform dispersion causes grain size refinement and so hole patch strengthening. Also, since residual dislocation loops formed around silicon dioxide nanoparticles, Orovon strengthening occurs. This strengthening improves yield strength, ultimate compressive strength, and fracture stress. However, adding particles more than 1% volume causes agglomerations which act as stress raisers, and this decreases the fracture strain. As we can see on the X-ray diffraction, bezel plane intensity peaks in 1.5% volume silicon dioxide. Most of the magnesium-based materials usually experience pitting corrosion, which is caused by localized fluctuations in the alloy compositions. However, immersion studies show us that adding silicon dioxide particles to magnesium decreases the corrosion because of uniform distribution of nanoparticles, and nanoparticles enhance the passive layer formation. As we can see, magnesium 0.5% volume silicon dioxide has the best corrosion rate. Besides enhancement of corrosion resistant and mechanical properties, research on mice showed that 95% of silica particles can be discarded from the body by feces and urine. Also, biocompatibility of magnesium silicon dioxide can allow cell survival and cell proliferation. The best rate of cell survival observed in the magnesium 0.5% volume silicon dioxide, and we can see cell cultured on the samples in figure at right. Nearly no dead cells and best cell proliferation seen on magnesium 0.5 volume silicon dioxide. As we can see, magnesium is a pioneer material in biological application when it's reinforced by silicon dioxide particles. Difference in the portion of silicon dioxide in magnesium also causes changes in material properties. And mechanical tests, immersion studies, cytotoxicity tests show that magnesium 0.5% volume silicon dioxide has a huge potential for clinical applications in the future. Thank you for listening.